Connor, are you all set for us?
Yeah. Can you hear me okay?
We can, Connor. That's grand. And it's yeah, take it away.
All right, excellent. Let's just set this up. Cool. Yeah. Thank you very much for inviting me to talk to this. I'm just going to be talking on this idea of mass customization of respiratory protective equipment. Some work that we did as part of a project called the Mensura mask project that was run due to and during the COVID pandemic. So this is going to be a bit about, we've had just two great presentations already explaining design automation and what goes into design automation. This is probably a bit more of a case for why and where you want to use it. So we went about looking at respirator masks due to the kind of sudden media attention and shortage of them for healthcare professionals during the pandemic. And we wanted to see if we could create something different that was better than the existing models. And during that journey, we learned a lot about the existing design methodologies that go into respirators and the need for automated design processes and mass customization. So, quick reminder of what we mean by a respirator. We're talking about these kind of products. So this is on the left is a single-use disposable respirator, an FFP3 or N95 mask, and on the right that's a elastomeric half mask. These kind of products, they rely on three core factors for successful performance. The first is compliance. Somebody's got to wear this product or use this product correctly for it to operate correctly. The second is they need to be comfortable. And if they're not comfortable, people are unlikely to use them despite the health benefits. And this was an area that was really highlighted during COVID because people are now having to wear these products for prolonged periods and for periods much longer than they would have before. And we saw images like this where this unfortunate individual has suffered from skin damage from wearing a respirator mask. And during our investigations, we found that high numbers, nearly 90–95% of all users of respirators reported some level of skin trauma. The third factor, possibly the most important, is goodness of fit. So unless a mask fits properly, and that for this type of product, it means creating a good seal around the interface where the mask and the face meet. If it doesn't create a good seal, then you'll get ingress of unwanted material, and then it's not performing its proper function, regardless of how good the filters are. So you need goodness of fit. And for healthcare professionals that have to wear these on a ward where it is deemed a safety item, a PPE item, they will undergo a safety test. And these tests determine whether or not the product fits your face properly. If it does not fit your face properly, you cannot be deployed on the ward. And obviously during a pandemic where suddenly all of the wards require, or many more of the wards require these devices, many more of your staff need to pass these tests. And what we found was that there were actually significantly high failure rates across the country, actually globally. And in some cases, we found reports of up to 90% of staff in a single hospital failing these tests for an individual make or model of a respirator. These high failure rates were attributed to high variance in facial characteristics arising from different demographic groups. And in the UK, we found that female healthcare workers were twice as likely to fail the fit test compared to their male colleagues, while other studies showed strong associations between race, resulting in statistically relevant differences of around about 25%. NHS, this is significant, as 77% of the workforce is female and 22% is non-white. So this represents a high risk for an organisation like the NHS, that in a pandemic crisis where you need a significant portion of your staff to be wearing these items of PPE, you suddenly have a far fewer staff available to you to deploy where you need them. So you are increasing the risk to those that you can deploy because they have to stay in the areas for longer. You probably affecting morale, working hours and so forth. So all round it's not a good thing. The reasons we found for these high failure rates, or why such a simple looking device such as a respirator was failing so many people, was historic shortcomings in the design methodologies that were employed to design these kind of devices. So to date, the key strategy for designing respirators has been modularization. So that is anthropometric sizing, the idea of classifying anthropometric characteristics of a population into a few represented groups. So essentially coming up with the fewest sizes needed to cover the largest population or potential population that you are providing to. However, no respirator design study has carried out the kind of population study, the size that would account for the breadth of variation in facial characteristics that you see from around the world. And in a country like the UK, where you have a very admixed population, that's a very large, wide demographic set that you need to account for. In order to do that, you would have to have a population size in your study that would be vast and would require significant, huge amounts of time. It'd be labour intensive, it'd be economically, it would be cost prohibitive. So we need to look for alternative design methodologies. Just as a sort of quick reminder, I might be teaching a few people to suck eggs, but quite what I mean by modularization, this is a concept that's been around for many decades, but essentially this is creating only a small number of products or product variation, which gives the sense of choice or variability to your customer base, such that we feel like we are able to find a perfect fitting model to us. I always think clothes are a fantastic example of this, that we go to the shops, we have set sizes, but there's enough variation between the cuts of different manufacturers and these sizes that we feel like we can find our own custom outfit. However, it's not quite a tailor-made suit. So modularization is always going to be limited by that anthropometric population data set that is used to create those sizes. Whereas customization infers that each product is going to be bespoke. Each one will be tailor-made to the individual. And we found quite a few studies during the pandemic offering methodologies to create custom respirator masks. However, all of these relied on a manual design process, skills-driven design process, access to CAD as well. So there was a lot of barriers before a clinician or a healthcare professional would be able to access a custom-made respirator. And really what we're trying to get to is this idea of mass customization. So how do we create that sense of variety and ease of access that you get from modularization, but be able to provide a custom-made, bespoke product to each individual at the same kind of cost and viability. Well, we do that by taking the current manual design process and replacing it with an automated one. Why do we? Well, sorry, yeah. So I think we've kind of seen already in the last two presentations a great explanation as to what goes into an automated design process. So I won't press on that too much. But essentially, we can kind of break it down to these sort of 4 steps of you need to require the data that's going to drive your design. In this case, we used mobile phones to collect 3D scans of people's faces. You need to manipulate that data and extract the bits that you need to drive your design process, so the parametric part of your CAD model. We built a fully automated design pipeline for respirators. The right-hand image is an example of one of the results. This was completely automated, completely seamless within one platform. From data input, so once a user submitted their 3D scan, all the way through to the 3D printed part, there was no human intervention in that process whatsoever. I wanted to just include this in the next slide as a sort of additional point as to why this sort of type of automated design pipelines and mass customization is important and how it relates to additive manufacturing. We often see this figure used that sort of describes the difference between traditional manufacturing processes and additive manufacturing in the terms of cost benefit for low and high batch numbers. And this is true for the case when we have the same design going through. So where we are repeated the same design, the same output, then a mass production process is more beneficial. When we move to a customized process where every design is going to be different, then conventional traditional manufacturing process mass production becomes cost prohibitive. However, this doesn't include the design process. And this y-axis, this unit cost bit, that's going to shift up and down dependent on how automated your design process is. So there is a strong need to automate as much of that design process as you can to reduce the costs as far as possible, to remove skill reliant steps, which are effectively where the costs are associated. So to summarize from our study, we found that current respirator design methodologies suffered from inherent design biases, which led to high fit test failure rates. Female and BAME users are poorly catered for due to these inherent weaknesses in the design process. And new design methodologies were required to overcome these limitations from modularization. Whilst customization offered a solution, it's reliant on manual and skill-driven processes. So we developed a mass customization, an automated mass customization platform that we successfully demonstrated as a proof of concept. That system didn't require any CAD know-how or human intervention once the 3D scan is submitted. It offers viability in terms of speed, scale, and cost, particularly in a pandemic crisis, for the manufacture of customized goods. And what would add as well is that all of the equipment that you need to collect that data that's going to drive your automated processes is already available to us. So we use mobile phones in a number of our projects to sort of drive these processes. And we all have a mobile phone now. So it's very accessible to us. Since this project, we've used the same key principles and looked at transparent facial orthoses as part of the RAHN sort of seed funding. And that project's just that came to an end last year, and we're just publishing some work from that. And it followed the same sort of workflow, and we had a nice success from that project as well. We've also been looking at using X-ray images to drive automated design processes for implants, and we heard earlier about orthotics as well. So really, once you have that initial data, you can drive any customization process you want. All from me.
That's great. Thank you very much, Connor. That's excellent.